So second morning talk by Markus on algebraic national.
Okay, so thank you very much for inviting me and for the kind introduction. So to all the people home, this is not my Apple computer, right? I just have to stress the Simons Institute forced me to use an Apple device. My laptop didn't work, and I'm sure it was not a fault of my laptop. So this is joint work with Christian Ickenmeyer, whose visa application was just received by the embassy, so he's not here. Gaurav Jindal, Vladimir Lyshikov, who's now in Copenhagen, Anurag Pandey, and Frank Olaf Schreier. And so I'm talking about various topics, testing membership in algebraic varieties, which you could think of ideal proof systems in some sense, algebraic natural proofs, and also some light connections to geometric complexity theory. But I'm trying to keep this at a rather high level because this is a quite mixed crowd here. So at least everybody should take something away from this talk. Okay, so natural proofs. There's this concept of natural proofs, which goes back to Razborov-Rudich as an explanation why we are so bad at making progress in improving circuit lower bounds. And they defined it as this concept of natural proof or natural property, which are somehow distilled out of the known proofs at this time and trying to describe why you could not make progress. So essentially you have three properties. You have a property P and you call it natural if these three properties here are fulfilled. So it should be useful in the sense that polysize circuits, functions computed by polysize circuits should have this property because you want to prove a polynomial circuit, a super polynomial circuit lower bound. So this property should be fulfilled for all these functions. You want this constructivity. Maybe you don't want it, but proofs typically give this constructivity property. That if when I give you the truth table of the function, then you can decide whether the function given by this truth table has this property in size, which is polynomial in the size of the truth table, not in the size of the input. And you have this largeness condition that because random functions typically don't have polysize small circuits, so random function should have this property, at least this is what you would expect, should have this property with at least 1 over poly probability. And essentially they studied known lower bounds proof at that time, and they came up that all the lower bounds proof at this time, or almost all of them, they satisfy the three properties. And then they essentially proved, or it's a very short paper, but a very fundamental one. They essentially showed that when you can use this property, this natural property, to distinguish pseudo-random functions from that have polysize circuit from a truly random one. Then, if you believe in public key cryptography, then this would at least some version of public key cryptography. Then a natural proof essentially breaks this public key cryptography. So no natural proof will show a super polynomial circuit lower bound. And if all the proof techniques that we know have this are natural, then we are somehow doomed. So you have to come up with some proof technique that at least one of these three properties cannot be satisfied. Most likely it should not be usefulness, right? Because you want to prove a super polynomial size circuit, a super polynomial circular bound. So it should be one of these two other properties. And we are also maybe not as bad as in the Boolean regime, so I can claim that because I'm from the algebraic regime, improving lower bounds in the algebraic world. So maybe a little bit better there. And but still, right? So we didn't separate VP from VNP, and we don't have any super polynomial lower bound for some explicit polynomial. And you can ask, why is this the case? And this led to the concept of algebraic natural proofs, which were defined by Forbes, Spilker, and Falk, and in parallel also by Grosho, Kumar, Sachs, and Saraf. So the first paper made it into into stock. The other one was just a technical report, so that's live. But essentially, they're both developed at the same time. And essentially, they had the same definitions were in there and the same conclusions. Maybe the only difference is that Forbes, Spilker, and Volk looked at more examples, but this was maybe the only difference. Okay, and so what is now our setup? So essentially, we have some class of polynomials. Let's call it C, and C is just contained in the linear span of some monomials. So you take a bunch of monomials. In the easiest case, say you take all the monomials in n variables of degree at most d. That's maybe the most general. That's the case we are typically interested in. And then we have a class of polynomials, which is contained in this linear span of these monomials. And now we have a second class of polynomials. Let's call it now D. And D is now essentially, you should think of this being a polynomial in the coefficients of the polynomials in this class C here. Right? So this is in some sense something which was the truth table in the Razborov-Rudich result. So essentially for every monomial m, we have some variable Tm here, and you essentially want to plug in the coefficients of the polynomial C here into the polynomials from this class D here. And then definition, so a polynomial D is an algebraic script D natural proof against this class C if the following two properties are true. So D is the non-zero polynomial, and for all f in my class C, D vanishes on the coefficient vector of f. Essentially, now you can use this polynomial D. It somehow gives you, this is essentially the property P that we have. So it vanishes on all these functions, so f, so all these functions f have the property. And because D is now a non-zero polynomial, you can use it to find a polynomial on which D does not vanish and prove a lower bound. And if we take this one D, it will define the zero Z defines a hypersurface, so it's a variety. So essentially, we now later will be interested in finding points f that are not in this hypersurface. And also, in this Razborov-Rudich setup, you have these three properties. Usefulness, this would be the same as vanishing on all the coefficient vectors of C. You have this constructivity, we'll come to that. And you have this largest condition, right? A random function should satisfy this property. And this comes for free in the algebraic setting. At least, so I'm typically interested in infinite fields, maybe even algebraically closed. Right, so and then the largest comes for free because lying outside almost all of the points, they lie outside of D. So this hypersurface defines as a risky closed set, and this has smaller dimensions. So almost all the points lie outside. In particular, yeah, we know well, a random polynomial is hard, but the questions have to come with an explicit one. Yeah? There's of course this constructivity questions. Of course, now how hard is it to check whether D of f is 0. And in this algebraic world, checking whether D of f is 0, it could mean two things, right? So I give you just a description of f, and you simply decide this question here with a Turing machine. But you could also think of this, you have a circuit for D, yeah? And then you could think about the circuit size. This could be different things, right? So talking about the circuit size of D, or just somehow checking this property D of f is 0. This could be different. This could make this here maybe more tractable in some sense. And then a hitting set for some class of polynomials P. So I have now a subset of polynomials P and new variables. Then a hitting set is just some bunch of points, such that for every polynomial P in my set of polynomials, there I find a point in my hitting set such that P of H does not vanish. That's the typical hitting set. And now to state essentially the barrier result of this in this algebraic natural proof business, we need this notion of what is called a succinct hitting set. We'll later see on that there can be very simple hitting sets, but somehow you want to have a succinct representation. The succinct hitting set is, so again, I have my set of monomials and I have my class C, which is contained in the linear span of these polynomials, and I have my polynomial D. And then this set H is called a C succinct hitting set for my class D if H is contained in C. So first think of H being, you can think of things being polynomials, or you can think of things being points by looking at the coefficient vectors. And then if I view H as a set of vectors of coefficients of length m, then this set should be a hitting set for my class D. Okay, so I have my small class C here of polynomials. I look at all the coefficient vectors, and if they define a hitting set for D, then this is called a C succinct hitting set for D. And now the natural proof barrier that was formulated in these two papers is the following. And this is it's a theorem, but it's essentially almost immediate from the definitions. But of course, it's the point is coming up, right? So getting the definitions right to come up with the theorem here, right? So if I have now my class C again, and I have my class of polynomials, I have my class of proofs D. And then essentially the theorem says there are algebraic D natural proofs against my class C, even only if there are no C succinct hitting sets for D. And that's essentially obvious, because being an algebraic proof means you vanish on C, but being a hitting set means for every polynomial in D, there's a point in C where it does not vanish. So therefore, that's the proof of the theorem. And as I said, the hard part is coming up with these definitions, getting the definitions right. Yeah.
So in what sense is this a barrier? In that, is there any reason to believe that C succinct hitting sets for D exists under certain circumstances? So this, it's like
that's yes, that's a good question. We'll come to that on the next slide. Essentially, the same happens. Now you look at all the proofs that have been done so far,
right.
circular law bound proofs, and they all produce succinct hitting sets.
Yeah. So, but then there's the other side where you say if there's a one-way function, then there is no natural property. Is there anything like that where under some widely believed assumption?
No, there's no formulation of some pseudo-random function in the algebraic set, right? So therefore, it's stated here, right? So you could now say this is either a conjecture, it's a wish, or it's a fear, depending on what you want, right? Whether you want to have small hitting sets or whether you want to prove circular law bounds. It's one of these three things. But there are no small polyglot succinct hitting sets against the polynomial size circuit. So this is and in the paper of Fox, Spilker, and Folk, they showed essentially that for most known proof methods, they are natural at that time. So they looked at all the lower bounds proofs, like in the Razborov-Rudich paper, and all of them essentially exhibited small succinct hitting sets. But there's no, this is maybe a point where there's maybe more hope. So there's no notion of a pseudo-random function or something like this in algebraic sets. So
could you say something about the difficulty of formulating the RFGs in the algebraic setting? I don't. Why aren't there pseudo-random functions in the algebraic?
So what would be a pseudo-random function? So what is a random polynomial? The first question. And then essentially you have well, you can of course say you fix the input set to be a Boolean cube, but then essentially this makes the question it's not an algebraic one anymore, not a purely algebraic one. Yeah? Of course, if you just want to say I want to have a bunch of polynomials, I want to have polynomials on a Boolean hypercube, which behave pseudo-randomly, that's of course that's doable, yeah, sure. But if you now simply have a polynomial, what does it mean to be pseudo-random? Yeah, of course, over finite field you have a function, then you're in the function domain again, right? But so infinite fields, algebraically closed fields.
In terms of
like when C is like, let's say DP or something, is it clear, like non-constructively, that there is a natural property that has like low degree, like maybe not small circuit size, or do we? Yes.
That's a very good question. You are talking in the afternoon, right?
Yes.
Yeah, so you get the answer in the afternoon.
Oh, okay.
Yeah. Yeah. Okay. Okay, so essentially we did this, right? So now in the typical domain, you have n variables, you have degree d, and then you want to look at, say, poly ND, that's the most general, or the setting you want to look at poly-sized circuits, and then there are essentially, then there is an algebraic polynomial n, capital N, which is just this binomial coefficient, which is just the dimension of the class C. Natural proof, you can see if there's no succinct hitting sets. And yeah, this is I also want to make, what you of course have here, you have this exponential gap between the succinctness of the hitting sets and between the size of the circuits. But in the algebraic setting, you can also do different things. You could even look it makes sense to look at regimes where you just have a polynomial gap between the class C and your proofs, right? And for instance, so tensor rank is such an example. We have tensor T is just some object living in a it's just a three-dimensional array of numbers. So you could think this of a generalization of matrices. We just add one dimension. And then you can also define rank 1 tensors, like you can define rank 1 matrices. Just the only difference is now you essentially take 3 vectors in the three ambient spaces, and just take the pointwise products of the entries, and then you get the entry in the corresponding position of the array. And then the rank of a tensor T is the smallest number of rank 1 tensors, so that you can write T as the sum of these vectors. Very natural notion. You have a complicated object and you want to construct it from simple ones. And then SR will denote the set of all tensors of rank at most R. Of course, I'm now talking about tensors, but you can also think of a tensor just being a trilinear form, right, where you just take this thing here as the coefficient of xh times xi times yi times zj or something like this. So we're just still talking about polynomials also, or very simple polynomials, so trilinear forms. Also, I will just talk about tensors. Then you can say, for instance, so D is just a poly-sized natural proof against my class SR. If D is non-zero, D vanishes on this class SR, and D is computed by a poly-sized circuit. And now here in this setting, so we just have a polynomial difference. So this is just a cubic number of variables more than the variables in the trilinear form. This of course also shows some of the problems. So the good news is, so tensor rank is a hard problem. So deciding whether a tensor has rank R, that's NP hard to decide. It's even harder. So it's hard for the existential theory of the corresponding. It's equivalent to the existential theory over the corresponding field. But that's good because this somehow could evade constructivity, right? Because now it's hard. There cannot be a polynomial sized circuit or some algorithm, polynomial time algorithm. But also some bad news, right? So I want to prove that some tensor doesn't have rank R, but SR is not the zero set of, it's not a variety, so it's not a zero set of a set of polynomials. But my proofs, they are algebraic, so they are given by polynomials. And if they vanish on SR, they will also vanish of the closure of the set of SR. But you could think of the Zariski closure, or essentially just take all the points. Let's say, think over the complex numbers. You can either say it's just the smallest variety that contains SR, or you can simply also take just the Euclidean closure. It's equivalent over the complex numbers. And this class, let's call it XR. And this is now a variety, and this is what is the so-called border rank. So this is describes all the tensors that you can approximate arbitrarily by tensors of rank R. And this is not the original problem anymore, because now XR contains tensors which have rank, you can prove that, which have rank greater than R, at least for some R, or for most R. Therefore, you cannot expect somehow with an algebraic proof to prove that the rank is greater than R. We can only do it for the border rank. Unfortunately, so at least we don't know whether border rank. So I would say we all think the border rank is an NP, deciding whether the border rank is bounded by R. At least I think this is it's a hard problem, but I'm not able to prove that, and I think it's still unknown to my best knowledge. So this is a problem. So one could study is tensor border rank is this an NP hard problem.
Is it in NP?
I don't think so. At least for infinite field. It's not. I don't. There's no proof that it's not an NP, but it's very unlikely. Yeah, because so tensor rank it's as I said the existential theory over. So even guessing a proof, right? So you need to guess real numbers, for instance, or complex numbers.
Yeah.
So unlikely that's an NP, but I cannot formally prove it.
Question is tensor in the existential theory, or do you need
No, it's in the existential theory, because essentially you just ask, if you look at this definition, right? You can just ask, do there exist S1, S2,
Sorry,
S3?
I meant border rank. That's what I meant. Sorry. Is the border rank in that?
Border rank, I think you need one quantifier more, because you need a universal quantifier to state that you are dense in the set.
No, but you can give the polynomials in epsilon. Huh? You can give the polynomials in epsilon.
Give the polynomial in epsilon.
So we don't need to bound it.
Yes, of course. If you state it in the algebraic definition of yes, you're right. So you can also state it if you state it in the algebraic definition where you write it as polynomials in epsilon, and then you can also even do this extension. Yeah, you're right. Okay. Okay, and essentially now what we are interested in, want to check so when a point is contained in some variety. So this is somehow the question that we have to deal with. Yeah.
What kinds of things do you want to work on for rank, or let's say border rank? Because natural proofs is like you're trying to prove lower bounds against some model, or
yes.
So what kind of lower bounds? I mean,
essentially, I want to have some explicit tensors. Any tensor where you can write down any family of tensors where you can write down the coefficients in polynomials.
oh, we don't wait, but the identity has high rank, right? You know, it's not.
The rank is just n.
So
Superlinear.
superlinear. So this is what we're interested in. Superlinear. So yeah. And so the identity, of course, the identity is rank n. We want to have something superlinear. So the best known lower bounds for tensor rank, there are something like 3n minus epsilon. So this is essentially this is the sum of the three ambient spaces. That's what we cannot exceed. Yeah. Even if you would prove 3 plus epsilon times n, and this would already be a breakthrough. Yeah, we should be able to achieve this. That's 4 years now.
The random tensor has rank n squared.
Random tensor.
Which tensor?
A random tensor.
Random.
That's a,
Random tensor, yes.
but you don't actually want to compute rank, right? Here you just want to prove for some explicit tensor that has high rank. So the fact that that it's NP hard, does that
Yeah, that's somehow good, right? Because you will always have to deal with this. So somehow you want to evade constructivity. And I have usefulness and I have constructivity. Usefulness I surely want for sure I want to keep. So somehow you have to evade constructivity. So all the properties that you are checking against, they should be somehow hard.
Is tensor rank useful against some circuit or classes? I guess it's the what I'm interpreting the question. So
yes, so you can prove superlinear bounds against trilinear forms, for instance.
What sort of gaps do we know between Tensor rank of border rank.
You won't did it. I think you can. The problems, of course, you need to prove the lower bound, right? So on the tensor rank, which already limits our knowledge. I think you can come up with a family which has a tensor rank almost 3n, and the border rank is n. And which is optimal given the message that we currently have. I think that was done by Yvonne. Good. Okay, and just somehow, yeah, so I want to study this variety membership problem. So given some variety V and some point x in the M space, decide whether x is in the variety. It's a good thing, of course, of thinking, right? So of ideal modular radical, this is essentially something like an ideal proof system, right? Because you want to check, here I want to check given a point whether it's in the variety. Yeah? And what is the complexity of this problem? And if somehow the answer is that somehow depends on the encoding of my variety. For instance, if my variety is given as a list of arithmetic circuits, then the membership problem is in co-RP. Because I can just take the circuits, compute the equations of my variety, and then I simply check whether all of them are 0. And I can simply use PIT for that. So if my variety is given by arithmetic circuits, then it's an easy problem. But of course, there are other ways to give varieties. But maybe before, I just want to briefly mention. So coming sometimes up with some, so we have the succinct heading set. So coming up with some heading set is sometimes easy, yeah? Because I can always give you a point where a polynomial that's non-zero, if I have the circuit, if it's given by a circuit, like before, yeah, I can always construct a point such that if my polynomial vanishes on this point, then it's a 0 polynomial. For instance, if I have just some circuit that computes some polynomial, and then if you take this point here, it's a huge point. But if f is non-zero, it will not vanish on this point. Which you can prove either by, I think it should be even possible to prove this by induction. Otherwise, there are some bounds like Mignot bound or something from univariate polynomials, roots of univariate polynomials, which essentially tell you that the polynomial cannot vanish there. Because some I just transformed this polynomial into a univariate one, and then I just put in some point which is so big that the polynomial cannot vanish there. That's really good and well understood. So coming up with some hitting sets, it's easy in this case. It's just a 1-point hitting set. But of course, just checking this here, right? That's not so easy, right? So we need again randomness to do this because we want to compute maybe a modular random prime. But there are further ways to specify varieties. So you could explicitly encode it into the problem, which is say the border. So you would just say the border tensor rank problem. That's an explicit encoding. I give you a tensor, I give you a number, is the border rank bounded by R or not? Then there's an interesting one, but somehow I already used half an hour. You could can specify varieties by orbit closures. So you'll see some examples in the further slides. So I have some group which acts on my ambient space, and I essentially simply want to know whether my point, a given point V, or whether a given point X lies in the closure of when I let Gn acting on my point V. And this is called the orbit containment problem or orbit closure containment problem. And many problems, interesting problems, can be formulated as an orbit closure problem. For instance, border tensor rank, you can formulate it as an orbit closure problem. At least some question of the VP versus VNP problem, you can specify it as an orbit closure problem or orbit containment problem. And there's a third way, and this is something some relation to hitting sets. You could give a variety by a dense subset. So I have some circuits, they define me some polynomial map. So just a bunch of polynomials. So just a bunch of polynomials mapping points to points, but just in each polynomial for one coordinate, I plug in a point, and then I look at the image of this polynomial map. And this should lie dense. So I can take the closure of this point set. Then I have a dense. Then it's essentially can efficiently generate a dense subset of my variety. And this you could think of as being some kind of fitting set. Because this polynomial map, if you run over all points, which is now infinitely many, in some sense, to define a hitting set. You apply the mapping on the left-hand side. You plug in all the points, so which are infinitely many. But I'm from algebra. I'm not afraid of infinitely many points. Then you just look at the image that you get, and you take the smallest variety containing this set. Take the Zariski closure. And for instance, you can define tensor rank or border, tensor rank and border tensor rank in this language. So I just take linear maps on my ambient spaces, and essentially, whenever I have a rank 1 tensor, I just let the first A act on the first vector, B on the second vector, and C on the third vector. And this gives me some homomorphism. And then I just, on arbitrary tensors, I do this by linear continuation. And then I say a tensor T prime is a restriction of T if there are such A, B, and C, such that you can write T prime as a restriction of T, as applying these three homomorphisms to T. And then you can put from the definition, if you can T prime is a restriction of T, it's somewhere here. Then also the rank of T prime is bounded by the rank of T. Because this thing here takes rank 1 tensors to rank 1 tensors. And if you take the decomposition of T, then you get from this the decomposition of T prime. In particular, there's what is called the diagonal tensor. So you just take the tensor is a big cube, and you just take from the one corner to the other corner, you just take a diagonal middle of 1. So you can think this of the generalization of identity matrix. Then you can prove that a rank is bounded by R if and only if T is a restriction of this diagonal tensor.
So this diagonal tensor is in a bigger space, though. So
this lies in a bigger space. So U and U prime, there could be different spaces. But then in the end, I simply want to identify U prime as a subspace of U to be back again in this space. Yes. And now essentially I can take all these endomorphisms. So now I'm identifying U prime again with U, that's here, and V prime with V, and so on. And now I can essentially take the endomorphisms of these spaces, and I can act them on like 1 tensors by this, and then by linear continuation. And then essentially the rank of a tensor is bounded by R if and only if it's contained in this orbit of the diagonal tensor where let act the endomorphism, the triple endomorphism monoid onto it. Well, this says nothing but T is a restriction of R. It's just rewritten in a more fancy language. But this is while this looks nice. So from a mathematical point of view, this is not nice because this is not it's not a group under composition because there are no inverses. This is essentially why we also here want to switch to border rank. So you can now replace, if you use border rank, you can replace this endomorphisms by invertible linear maps, so by GLR. So GLR are just all the R cross R invertible matrices. And then you can reformulate the result on a previous slide for border rank, just that the border rank of a tensor T is bounded by R if and only if T is contained in this orbit closure here. We can formulate the border rank problem as an orbit closure problem. And there are many other ways how to formulate interesting problems as orbit closure problems. So there's this lemma by Valiant that whenever you have a polynomial which can be computed by a formula of size S or even an ABP of size S, maybe it's then there is some matrix pencil, so just some affine linear. So you could think of these. So these are now matrices with field elements of coefficients. These are variables. You could also think of this being a matrix with Fn linear forms as the entries. Yeah? And then every F can be written as the determinant of such a matrix A. And the size of the matrices is linear in the size of the formula size or ADP size. Then you can find some other action. I don't want to go too much into the details, but what you can show is essentially that when you have some group which acts on some vector space, then the null cone are all vectors V, such that the 0 point is contained in the orbit closure of this point V. And of course, this is here, of course, right? So deciding whether this determinant here is non-zero or not, this would be identity testing for F, right? Because so whether this has full rank or not, this is identity testing for F. Right? We don't know how to do this. Yeah? But now you can switch to the non-commutative case. So there's also some non-commutative version of the rank of a matrix pencil, which I don't want to define here. And then you can show that A does not have full non-commutative rank if and only if A is the null cone of some left-right action. A is in the null cone under some certain action here. Right? And this action is quite easy. Maybe I should also just explain this. You just take all these slices here, and then SLM, which are just all the matrices with determinant 1, they just act by left-right conjugation on all these 3 slices. And then you can show that under this action, A does not have full non-commutative rank if and only if A is in the null cone of this action, so that 0 is contained in this orbit here. And this is a famous result by Garkowitz, Oliveira, and Victorson, that this null cone problem can be solved deterministically in polynomial time. So for non-commutative rank, we have polynomial time algorithms. And so for border rank, we expect the problem to be hard, but the orbit problems, they are somehow fundamentally different. Because for the tensor rank problem, this here is fixed, and this here will be my input. So it's on the left-hand side. And for the null cone problem, this one here is fixed, and this essentially is my input. Right? So the points are flying fundamentally different. And this is the reason why, or maybe one of the reasons that this problem here is also a different action and so on, but this is some fundamental difference. And of course, 0 is also a very easy point, right? So this is maybe one of the easiest points that you can think of. Yeah. Yes.
Is it just the rank of A? What is
the decision question is, so here I want to decide whether in the commutative case I want to decide whether the determinant is of A is 0. Whether this pencil has full rank or not, which is identity testing for F. If A gives you the determinant of A is F. And now, so I want to decide whether this has full rank or not. And now I can define a non-commutative version of algebraic rank. Of matrix of pencil rank. And I want to test whether this pencil here has non-commutative rank, full non-commutative rank or not. And this you can do in polynomial time.
How about you want to check whether it's rank is if it has non-commutative rank in full star?
This should also be possible, but not by. Yeah, from this algebraic algorithms, I don't know whether you can do this with this operator scaling, but from the algebraic,
I think the
algebraic algorithms by
KV
and Ibanez and Piao, right? So Newman was around it. Yeah, they should also give you this one, but this is yeah. Good. And also, you can also write determinant versus determinant question as orbit problems. So running a little bit out of time. So in this VP versus VNP business, so our reductions, they're essentially projections. So we have a polynomial, you can replace all the variables by other variables or by a constant. This is very weak, but it was sufficient simply for Valiant to do his theory. So therefore I choose this one here. And essentially now we have a polynomial Fn of polynomials, and we have some polynomial Gn, and whenever I say P family, it means that the degree is polynomially bounded and the number of variables is polynomially bounded. We say that one is a projection of the other one. If I can write Fn, get it out of G, but just checking the projection of something which is just polynomially further in the sequence. And then you can also let act the endomorphism monoid act on my polynomials, and it preserves homogeneity. And this means that in this setting, if we're talking about homogeneous polynomials like the determinant, you would have to add some padding factor to make add up for the degree. But then so we can also get some algebraic version of Valiant's conjecture. When the VP does not equal VNP, there's something weaker. And this essentially, you can, so VS stands for weak dispute, is some restricted circuit. Okay, this is equivalent whether the permanent is not a P projection of the determinant. And this you can also formulate as a orbit closure problem. Essentially now let GL and squared act on the determinant. And then you want to know whether the padded permanent is contained in this orbit closure. And this is essentially VNP is not contained in the closure of VP weakly skewed. This is essentially this observation is essentially the starting point of geometric complexity theory, where essentially you want to disprove this thing here by now using methods from representation theory and so on. Yeah, because we are now dealing with hard problems, and somehow you have to also use some hard machinery. Yeah. And so therefore you want to understand that there were these fundamental questions. You want to understand the complexity of this problem, this orbit closure problem. And here I just want for the last couple of minutes to focus on tensors. So tensor rank is NP hard. Tensor border rank is unknown. But there's some variant of tensor rank, which is called the min rank, where essentially you just look at the slices of this tensor. So you can think of this being n matrices, and you just ask, what is the smallest non-zero linear combination? What's the smallest rank of a non-zero linear combination that you can achieve? Yeah? And this one is also NP hard. And for this one, the border min rank and the min rank, they coincide. So there we have one particular rank measure on tensors, which is nice in the sense that also the border variant is NP hard.
It's not like slice rank.
That's not slice rank. So essentially, you think of the tensor being n matrices, and you just take a linear combination of this, a non-zero one, and the question is, what's the minimal rank that you can achieve? Right? And by some compactness argument of because it's projective, the minimum is essentially attained in the closure, not in the closure, it's in the set itself. Let me. Switch here. So this is essentially the general setup. So we have a sequence of varieties. We have a sequence of points. These varieties might be given by orbit closures, and we want to prove that X is not in V by exhibiting some sequence of polynomials that doesn't vanish on the point, but it vanishes on this variety. And this Fn is essentially this natural proof that we had in the beginning. And we want to understand what's the complexity of Fn, because most likely it will be super polynomial if this membership testing is hard, and if we want to weight this constructivity. Essentially, here's essentially two more definitions. So we say a variability is polynomial definable if you can describe it by a polynomial set of equations that are all polynomially bounded. Because you should think of this being the proofs that you are in the variety. And we say it's uniformly generated if you can generate a dense subset of a variety with polynomial sized circuits. So you have a polynomial map, which describes a polynomial sized circuit, and you can do this uniformly. And what you then can prove is that essentially, whenever you have some conditions on the field. Whenever you have such a sequence of varieties that's polynomially definable, and you can uniformly generate a Sten subset, then testing V membership problems NP-hard, and the V membership problems NP-hard, then this means that co-NP is a sequence is contained in there is BPP. So in particular, the polynomial time hierarchy collapses. Essentially, you can do this by essentially you're guessing a circuit, so you're guessing a proof, and because because this variety is polynomially definable, this proof is polynomially long. Then you compute polynomials which generate the Sten subset. Then you can use polynomial identity testing because you have this BPP to check whether our circuit is identically zero on the Sten subset, and then it also has to vanish on the whole variety. Yeah. And otherwise, because now my V membership is NP-hard, you can take some reduction of your whatever is satisfiability to this problem, so you get some point, and you want to check whether this circuit now vanishes on is in the variety, and you can now do this by take identity testing, polynomial identity testing. Yeah. And this way, you have now reduced an NP-hard problem to some algorithm here, which is an co-NP. Yeah. Because membership testing is the yes instances they are outside. Yeah. And let me. And the main ingredients essentially that we have seen here is this polynomial definability, which essentially gives you the assumption, or it's some lower bound. Yeah. And you have this uniformly generated. You could think of this being, it's a little bit stronger than a hitting set generator, but it's typically achieved, for instance, easy to achieve for tensors. Yeah, so for instance, for tensors of rank R, you can simply take the sum of R generic rank 1 tensors. This will essentially generate you SR. And the hardness of the membership thing, this is the third ingredient. This needs an individual proof, and this has some somehow related to the minimum circuit size problem, right? So what is the smallest tensor that generates my Trellinger form? This is some version of the minimum circuit size problem. And if we have that this is NP-hard, we have this for tensors. We know that tensor rank it's uniformly generated. Then the only conclusion, if you believe that pH is infinite, means that you cannot describe the variety of tensors of order rank R by a polynomial set of equations that have all polynomials. I think I'm already a little bit over time. This is the min ring. No. Let me briefly, so I have to skip a little bit to conclude. So for the min rank, everything works. So for border rank, we don't know whether it's NP-hard, but you can do the same for min rank. Then of course you can ask, can you still prove lower bounds? Are there methods to prove lower bounds for certain tensors there? And so this is then essentially where GCT starts. And we can construct essentially various equations for min rank varieties using GCT methods, even in the regime where the membership problem is NP-hard. But then, of course, the problem is you need to prove that the instances that you get out of this NP-hardness proof, they don't they're the equations that you construct, they don't have to vanish. And that's the hard problem. So you can describe them succinctly by some succinctly represented exponential self-determinants, some succinctly represented exponential sums, or some representation theoretic objects like conical coefficients and this stuff, but which have been studied since 150 years. Yeah, but then you go to a mathematician who's studying these objects for 150 years, and you just tell him, here's my object, here's my point, does it bench on this? And he says, how shall I know this, right? So we are only looking since 150 years on this problem. That's way too advanced to solve this. Yeah? So the upshot is, so GCT gives you methods to come up with small-sized objects that could be a proof, yeah? But these proofs, they're incredibly powerful in the sense that even mathematicians don't know whether this thing is zero or not, right? So, so it's not only about the size of your description, but also essentially on how efficient are you able to evaluate this, right? It's like in the end, it's like you could also have a small size for permanent if you have a permanent gate, right? So this is essentially the same problem that we're facing here. Yeah? And the only conclusion that I can draw from my talk is essentially it's a hard problem, right? So, and that's it. Thank you.
Good questions for Markus. So can I have one question? So is there any notion of rank where the border rank is not equal to the rank, but the border rank is not going hard? So you mentioned the bottom mid rank, but that's because bottom mid rank is equal to it.
Yes.
Are there any notions of rank where the border rank is not going hard without the border rank being equal to it?
Not that I'm aware of, because we do see some talks in there, and it's very hard to understand these closures, right? So this is it's a super complicated object, and the only way you need to have an NPR problem, and someone want to encode it into this rank problem, and then the non-border rank version you typically can understand because it's still an algebraic object, but it's defined pretty concretely, right? So there's a vector such that the linear combination has rank R or something like this. So there are rank 1 tensors such that the sum gives the object. And this you can understand, but then if you take the closure of this, it is very, even for simple dense sets, it's very complicated to understand these varieties. And at least the only trick that I know is you find it in the right way, that the thing is compact, and then you know that the closure coincides with the tensor.
Thanks, Markus.